by 64 array of these processing elements. And it's designed to sustain a throughput of about 2 teraflops per second. And in order to help us achieve that, Google puts about a 4 megabyte on-chip buffer distributed in various ways within the chip today. And there's a specific data flow which I can't talk about too much because of, unfortunately, proprietary restrictions. But you can imagine that these, like most accelerators that are out there today, have a fixed data flow, where you will try to maximize reuse of some of these elements that we're using for the machine learning models, and then we try to broadcast some of the other ones to reduce both the to maximize locality and to reduce the amount of operand communication you have inside the chip. And so we looked at 24 of these edge neural network models, and we looked at a number of different domains. Again, those 4 big uses we looked at models that were used for those and for other use cases. And unfortunately, we can't say too much more beyond the fact that we've looked at all these transducers, LSTMs, RCNNs, and the typical CNNs. But they are models that are either used in production or are basically facsimiles of production inference models that people are using on their mobile phones today. And as we did our characterization, I'm only going to summarize the characterization. There's more details in our FastPath2021 paper if you're interested. But we found 3 major challenges for the edge TPU that held it back from achieving maximum throughput, maximum energy efficiency. So the first is that despite having provisioned this efficient device for the edge, we still see a significant shortfall in the throughput that this is supposed to be able to achieve. So we never actually get close to that 2 teraflops per second that I just mentioned. We also find that despite this device being designed for efficiency in mobile devices, it operates significantly below the peak achievable efficiency that it should be able to attain. And the third challenge, which is in part, large part responsible for these first 2 challenges, is that this actually does a very poor job of handling the memory accesses for many of these newer types of models that we're seeing. And so I'm just going to go through a few roofline graphs summarizing some of the characterizations that we've done to give you a rough idea of some of the shortfalls that we see. And so on this roofline, you'll see on the x-axis, I'm showing you the number of flops per byte that we get. On the y-axis, we're getting the teraflops per second. And this dotted line is essentially showing you the achievable energy efficiency we can get through this efficiency we get through this model. And what we find here is that if we're looking at throughput, particularly with LSTMs and transducers, we do a very, very poor job of those in the edge TPU today. We're getting less than 1% of the peak throughput that the accelerator offers for these types of neural network models. And even if you look at the things that this is supposed to be good at, convolutional neural networks, we're still not achieving full peak. We're only at about half of the throughput that the TPU promises. Likewise, if we do the same thing and we look at instead of teraflops per second, teraflops per joule to look at energy efficiency, we find similar shortcomings here. LSTMs and transducers, because of the amount of energy they consume, they're only able to achieve a third of the maximum energy efficiency that the TPU promises us for these refined models. And again, even CNNs, we're still falling well short. The very best single CNN model that we evaluated was able to achieve just over half of the peak efficiency. So something's going wrong here. We're falling very short of where we're supposed to be. Well, that's where this whole idea of looking at the memory accesses comes into play. We did a detailed study on breaking down the different components of the network models and the type of I/O that the accelerator was doing, and we studied where the majority of the time was being spent in the application. And what we found was that, so I actually, green LEDs are supposed to be better on TVs, but apparently not on this one. But on the y-axis, I'm showing you normalized energy. On the x-axis, you're seeing the whole, each of the models that we evaluated. And what you can see is that the on-chip and off-chip memory traffic is actually responsible for a large portion of the inference energy and execution time that we're spending. You can see, we actually have the PE the processing elements that do the actual computation in blue, they don't even show up at all for the LSTMs and the transducers. It's just a small sliver of that total energy that's being consumed. And instead, if we look at the amount of energy being spent on DRAM and on the off-chip interconnect, we see huge fractions of the total energy being spent on that.
Sorry, quick.
No, of course.
How much does that vary, say, with model size or other? I assume the memory traffic is a bigger proportion of larger.
Absolutely, right? Unfortunately, we weren't allowed to be able to divulge the actual size of the models. All we can say is that some of them spill out significantly from the total capacity inside the accelerators. But we couldn't report exact numbers, unfortunately, as you can imagine. But yeah, the thing to keep in mind is that these were tuned specifically for edge inference. So this is already their best effort to try to get the models to fit as much as they can onto the edge TPUs. So what we see here is that, off-chip parameter traffic, sending stuff out to DRAM, that's costing 46% of the total energy that we're consuming just to run these models. And a further 30% of the energy is going toward taking all the data that's on chip and just distributing around from PE to PE or back and forth between the buffers themselves. Essentially, much like we've seen in many other applications in computing, the movement of data, both in the chip and off the chip, are actually dominating the costs here. And this is sort of a little bit of a surprise from machine learning, where we thought we were kind of immune to these kinds of issues, because we thought, again, the matrix multiply was the real source of energy consumption here. And so these are the three challenges we're facing. What we want to understand is why this is happening. What's the root cause behind all of this efficiency? Obviously, people that are working on this edge GPU are very, very dedicated. They're very smart people that have been working on this for a long time. Well, we find two things, and this is really as a result of the models that have sort of taken over in recent years for a lot of these types of functions. The first is that if you look from model to model, we have a lot more heterogeneity than we were used to in the past. And as you can imagine, some of this is because we have all these different types of models that we're dealing with these days, right? It's no longer just the CNNs. But one of the things here you can look, and this will get at some of your question, Eric, the parameter footprints that we have, right? It's not the total traffic and storage that we need for the temporary variables. But what you can see here is I've got the parameter footprint on the x-axis and the throughput, the number of flops per byte that I can get on the y-axis. And what you see is that there are sort of clusters that are showing up roughly in this graph. We see that a lot of the layers, and we look at individual layers, from CNNs and RNNs tend to be in the top left portion. They get reasonably good throughput, and they have reasonably small footprints. But in particular, when we look at the layers of the LSTMs and transducers, those have almost a flipped relationship. They're getting very poor throughput, and they have very large model sizes. And so as we go towards these new types of models, we're seeing a huge amount of pressure toward the memory system that we did not experience before.
I'm sorry.
No, of course. Go ahead, Eric.
So does this depend on your data representation? I mean, if you have 16-bit flow, 32-bit flow,
sure.
I mean, does it just scale pretty much linearly with as you change the sizes in terms of what you're showing?
I mean, we expect it to be not quite linear, only because you can imagine that if we approximate that the floating point units are going to behave linearly within precisions, which sometimes they don't, right? Yeah, then it should scale linearly with the size of the inputs, right? And so I believe all of these are with the typical pfloat 16s that they've been using inside the TPUs. And you can of course imagine if you go to integer, if you go back to the days of integer computation for machine learning models, you might be able to get much different trade-offs here in terms of computation. Yeah. If we stick to floating points, I would suffice to say that it's fairly linear.
So you're not crossing a boundary or something, everything fits in the GPU memory, TPU memory.
I mean, you could be on to certain points, but I think a lot of the issue is that the models have gotten to a point where just the amount of intermediate data that they're recording for partial weights and things like that, partial outputs and things like that, that still has to be kept someplace, and we're just starting to run out of provision at the local buffers. If we scaled everything accordingly and maybe redistributed some of the buffers, there's a chance you would have nonlinear behavior. But until we sort of revisit that holistically, I think it becomes harder to just like scale things down, slowly, and then hope that it comes back to some nice points. And so this is one of the issues. The second thing we see is even within a model now, given that we're trying to put a whole bunch of different types of layers together in these gigantic models, we now see significant variation in those characteristics. So let's take a look at CNNs, our good old friend that's supposed to be nice and easy. Even in those convolutional neural networks, we see that from layer to layer, the number of multiply accumulates that you are performing can differ wildly based on the type of filters that you're applying, the type of transformations and features you're looking for. And this depends on the model. These variations are very model specific. But some of the models we analyzed had up to a 200x difference between its highest macularization and slowest macularization from one layer to the other in the same model. And even if you look at how it translates to the total throughput, if we factor in the memory, we can see sort of up as much as a 244x variation in this. So again, we're seeing very large unexpected variations that we're not used to dealing with. So why am I pointing all of this out? Why am I talking about all of this variation that's sitting here? Well, this really gets at where the problem comes from. Essentially, we're doing the same thing now with our TPUs that we used to be doing with CPUs. We're throwing the one-size-fits-all hammer to a whole bunch of increasingly diverse problems, and now we're paying the prices of inefficiency that we didn't really think about having to deal with in the past. And this is because if you look at the structure, right, this is that same diagram I showed you, the really rough diagram of the TPU that I showed you at the very beginning. Nothing about this takes the different models into account. We have a fixed PE array size, we have fixed buffers, we have a fixed amount of object bandwidth, we have fixed data flows. Nothing is catering toward the different types of patterns and behaviors we're seeing inside this model itself. And it turns out that instead of actually thinking about this diversity, we've been, again, trying too hard to think about the one-size-fits-all problem. And so this PE array is oversized for even the largest problems that it deals with. Right? We were hoping that throwing PEs at the problem would take care of this whole issue, and it turns out that it did not. Unfortunately, that's the one thing that's over-provisioned. All of the other things are under-provisioned, and hence why we are spilling out to memory so often, right? But that's an under-provisioning not of choice, but of restrictions thanks to the limited resources we have. In a happy world, we throw megabyte upon megabyte of SRAM into these accelerators, but that's not the reality we live in today. And so the main point that we want to take away from this characterization is that now, in today's age, where we have a whole bunch of different use cases for machine learning, we can't stick to the single one-size-fits-all accelerator design. And so this is where we want to sort of bring PIM into the picture. Why PIM? Well, much of the problems of the one-size-fits-all model are with data performance. And if you've ever seen a PIM talk, you've probably seen some variant of this slide about 1,000 different times. Essentially, we're at this age where we got so good at optimizing computation that computation is now a small fraction of the total energy spent within a chip and within a system. So this is a slide from Bill Daly's keynote about 7 years ago now. And these numbers still hold if they have gotten slightly worse. Where essentially, moving data on chip takes anywhere between 10 to 50 times the amount of energy it takes to actually do the computation on not just any number, but right over here, a double precision floating point number. So already one of the worst types of addition you can do for a generic computation. This is much worse for DRAM. It takes almost 1,000 times the energy of that double precision floating point number addition to go to DRAM and back. And so we pay huge costs in modern systems. This data movement is a bottleneck both in terms of energy and in terms of performance. And it's not a new bottleneck. Even though we didn't think about it in the same terms, John Backus, when he was giving his Turing lecture in 1977, actually called this the von Neumann bottleneck. It's simply an artifact of the way that we've designed computers since like the 1940s. It just so happens that it worked really well when computation was the big problem. But as our data sizes have grown and as the applications we've been looking at have become much more data intensive, the von Neumann model starts to break down very quickly. And so this is what we're hoping to do with processing memory. Essentially, today, I have to take a piece of data when I want to do even the simplest of computations out of it, take it out of the DRAM, move it across a long, narrow memory channel through any SRAM in a CPU that be just multiple levels of caches, for the TPUs that be potentially multiple levels of buffers, until it gets to the processing to do a computation. Even if I use that value one time, I've got a great. The whole idea of processing memory is that we now have the capability of adding some form of computational capability in or near the memory itself. And so now, for simple computations, I don't have to move things around at all. And this generic story works very well in a number of different contexts. We can't go quite as restricted, quite as loosely as we want to do for other applications for machine learning. But I'll show you how we can apply this type of model in two different ways to actually improve the ML energy efficiency and performance. I just want to note real quick that this is not a new idea. PIM, actually I don't know if any of you were at the PIM2 workshop yesterday, but Peter Koh-Hughes, one of the, I'd argue, one of the fathers of, among many things, processing memory, was actually giving a talk there. And he did a lot of the foundational work on this in the 1990s, based on some of the ideas that his advisor, Harold Stone, had all the way back in 1970 on the logic and memory computer. So we've known about this bottleneck, we've known about the need to try to move things to memory for many, many decades. Unfortunately, we just haven't had the technical skills to implement a lot of the hardware that we wanted to envision with this kind of work. And so it's come and gone over the decades, but we've now finally reached a point in the last 10 years or so where new innovations in memory design have made this possible. And in fact, there are prototypes of this that you can buy today on the commercial market from companies like Samsung and by IBM. So we're going to look at two variants of PIM. And people have, since we're still a community that's rediscovering ourselves at some point, we have a whole set of different taxonomies for this. So this is sort of my view of how to classify PIM at a high level. The first thing is what I'm going to term processing near memory, PNM. Effectively, we can take advantage of the high internal bandwidth of things such as 3D stacked memories, or we can take advantage of internal memory bandwidth through things such as heterogeneous integration. Effectively, and I'm going to use the 3D stacked memory as an example here. 3D stacked memories such as the high bandwidth memory models that you can buy today stack multiple dies of memory together using vertical wires known as through-silicon vias. To give you a comparison, if you look at the memory channel that connects the CPU to a memory module today, you've got about 64 pins, so you get 64 bits of data in every cycle. Technically half a cycle, but I'll leave that detail out for now. Here, inside the 3D stack chip, I can support up to 2,000 TSVs across the layers. So we're talking, if I can do my math right today, about 32 times the bandwidth that we're seeing on the channel. And this, of course, depends on the type of memory technology, the array of the size of the arrays. But of course, to compensate for that, we now have micro TSVs that are actually shrinking the size of these metal wires that can get even further pins stacked vertically. The bottom line here, and the main takeaway, is that by exposing this internal bandwidth, I've got a lot more bandwidth than I can ever get into the package of a CPU. And so I can have, alleviate a lot of the memory pressure that I have today in a conventional computer. One of the things that we can do with this processing near memory is that we can either within the same stack, or again with heterogeneous integration with some sort of chip or die sitting nearby this memory, we can add logic that has access to all of this bandwidth. And so this means that we no longer keep it just for internal memory operations. We can now expose new types of parallelism and new opportunities for getting data at rates we could never do before. The second variant, and this diagram is perhaps not the most helpful, is what's known as processing using memory, or POM. Here we go one step further. So processing near memory is perhaps something that's feasible with types of integration that we're looking at today. POM, I'd argue, is perhaps a slightly additional level of crazy that we add into here. Where we say, instead of adding CMOS-like logic near the memory, let's just actually turn on memory cells at once, have them interact with each other. Oh, and by the way, when they interact with each other, it turns out that they're doing meaningful work. They actually can use useful computations such as Boolean algebra, or in some cases, whole multi-bit multiplies. So the second problem actually has a lot of interesting properties based on the type of operations you can exploit out of it. The thing to keep in mind is that you can do this with many different types of memory, but how you actually get that interaction to work is very memory dependent. So not every memory can do every type of operation. What's nice about this is that in this previous case, I have to add a whole bunch of discrete logic into this logic layer into a new die. I have to introduce new logic circuits. With processing using memory, there's not much to introduce. Aside from some control circuitry, much of the work is actually being done by the existing memory cells. And so we don't even have to move the data at all. We can just go directly into the cells where the memory and the data already sit, turn the cells on, and get meaningful work to happen with, I would argue, some of the most minimal data movement possible in logic.
POM seems like it's much less limited in terms of actual memory capacity. The stacked TSV approach is presumably limited by the way the cells shift physically.
No, actually, that's actually a very good point, right? Here, we're not limited to any of the types of stacking issues we have. There are other issues that we're going to talk about in a little bit today that actually do limit some of the throughput you can get if you're not careful about architecting around it. But yeah, at a high level, yes. We don't have to deal with the limitations of 3D stacking or anything that we need to deal with today. And I just want to make sure I've got an eye on time. We've got until 1:50, right?
Yes, and then actually 10 minutes of Q&A, so we can point out.
Okay, well, I'll try to keep that in mind. So the first thing I want to talk about is Mensa, which looks at that first variant, crossing your memory. Mensa, essentially, there's a reason I call it Mensa G on that side, but I talk about Mensa here. Our goal with Mensa was to build a framework, not a specific accelerator, that allowed us to manage multiple accelerators. Essentially, the problem with the Edge GPU was that it was a single model, a single hardware design, creating all these different models. So let's just fix the problem. Let's introduce heterogeneous accelerators. And so Mensa is a two-stage framework where we can introduce multiple accelerators for multiple different types of models. And in order to manage what model runs on what accelerator in the heterogeneous pool of accelerators that we have, we actually designed a software runtime that can study the model and study things on a layer-by-layer basis and figure out which of the accelerators to dispatch them onto. And it takes into account things such as, hey, I've got 2 layers back to back. Right? Is it more efficient to keep run this new layer on its most efficient accelerator, or is the amount of data movement to get information from one layer to the next going to be so much that we will instead run that layer on a suboptimal accelerator, but the same one that the previous layer was running? So essentially, we're making decisions not only about the optimality of an accelerator for that particular layer that we're accelerating, but also how much communication is happening between the layers and whether or not it actually makes sense to migrate to a different accelerator at any point. And so in the interest of time, I'm not going to talk too much about this runtime scheduler. There's more information about it in your paper, but it essentially at a high level takes the information I talked about, including a bunch of offline information that we figure out when we're setting up the system based on the hardware properties, and online information about the models as they're running, and then figures out that scheduling at runtime to dispatch layers to different accelerators.
Sorry, thank you.
Okay.
Design automation, this seems a lot like placement and routing.
Absolutely.
Which can be computationally intensive by itself. So it is what you just flashed up there is like how computationally intensive is it?
Not very, because we're generally talking about a very small number of accelerators that we're talking about here, right? In the example we're going to look at, we're looking at 3 of them. And it turns out that, as I'm going to mention now, instead of looking at individual layers and individual characteristics, we can actually group layers into families with common properties. And so in our example implementation, it was 5 families and 3 accelerators. So the search space is actually much smaller than you'd have for something like placement. And so that's actually the key observation that I have in this slide, which I'm also going to blow through in the interest of time. But essentially, we don't have to think about things on a layer-by-layer basis necessarily. We can have ranges of parameters because many of the layers have sort of clustered behavior. They operate what we call layer families. And so we do this analysis across a number of the different parameters that we were studying as part of our characterization before. And we come up with sort of 5 families that fall into 3 broad categories, or 2 broad categories. Families 1 and 2 are what we call compute-centric layers. These are the layers that don't do a lot of I/O. They still require a lot of computational power from the processing elements. Families 3, 4, and 5 are what we call data-centric layers. These are the ones with really large parameter footprints, poor reuse, and they don't really tend to use them multiply cumulative nearly as much as the compute-centric layers. And so these 5 families, and within the compute-centric layers and within the data-centric layers, there are different properties among each family, which is why we separate them out, which I'm not going to go into detail for here. But these 5 families sort of are what we're going to use to inform the way we design our accelerators. And so the idea here is that, okay, this is, we now have Mensa, this framework that allows us to have heterogeneity. The exact implementation of the hardware will depend on the type of models that you're trying to run. And so Mensa as a framework can adapt to new and to future models. Based on this information here, which is studying the layer families for the Google Edge models we looked at, we're going to use that to design an instance of Mensa called Mensa G that's designed for those edge models that we're looking at. And so when we study the families, we come up with 3 accelerators. Pascal, Pavlov, and Jacquard, I should say. First, Pascal is essentially the accelerator designed for the compute-centric layers. And so we find that we don't need the 64 by 64 PE array even for these layers, because as I mentioned before, the PE array was over-provisioned in the edge TPU. So we shrink this down a little bit to despise this area for some of the other accelerator layers. We have a smaller activation buffer in here because we find that we don't need a huge number of activations for Pascal and for the compute-centric layers. We shrink down the parameter buffer significantly. And we keep this accelerator on chip. So just like the edge GPU today is meant to sit close to the CPU, Pascal is going to sit close to the CPU as well. The next model we have is, accelerator is Pavlov. Pavlov is designed for some of our data-centric layers. Specifically, it caters to, but is not exclusive to, LSTM layers. In LSTM layers, we have a smaller PE array because they're not terribly computationally intensive compared to the amount of data that they need. We still have an activation buffer, but we get rid of the parameter buffer. The parameter buffers, no matter how big they are, have really terrible reuse in the LSTMs just because of the size of the operations that we're looking at. And so there's no point in wasting space on the chip for this when it's going to go to memory anyways. And so instead, what we do is we make this a processing new memory accelerator. We put this in that logic layer of that 3D memory, and then that exposes the high bandwidth to allow us to be able to get the throughput that we need to sustain to get much more efficient computational capabilities for the LSTMs. Our third accelerator is Jacquard. Jacquard is designed for non-LSTM data-centric layers. So it has slightly more PEs. They're not as, they have a little bit more computation, these other types of layers than LSTMs do. We still have smaller activation buffers, but we do see some parameter reuse, and so we do keep a parameter buffer around here. But we still have a need for a lot of data here, and the buffers, while they allow us to get some sort of reuse, they can't sustain it all. So we still place this accelerator near memory as well. And I have not gotten into a lot of details about this in the interest of time. These are just parameters of these devices, but in reality, we were very careful about co-designing the data flow to maximize reuse as we were sizing these memories. Right? One of the things that we think people often overlook is we think about data flow first based on the first principle reuse behavior that we see in these models. But in reality, the spilling out into memory actually has a significant effect on the type of reuse you can best use. And so we actually found that we had to co-design all of this, that whether or not it's memory, the size of the buffers, the size of the arrays, and the data flow as one holistic device, looking at how we actually interact with the memory system over time. And so, of course, this wouldn't be in our teacher talk if I didn't show you a bunch of graphs that claim that we do better. Again, in the interest of time, I'm not going to go through these in much detail, but I'm just going to summarize real quick that we cut down a lot of the energy that was being spent on off-chip parameter traffic. And overall, compared to the edge TPU, our energy actually reduces, it's not even, it's really the energy, but it improves by about 3.0x. Okay? So we can cut down the energy by 2/3 by using this customized heterogeneous arrangement. And we see similar gains in terms of throughput. So we have our baseline, the edge TPU, in gray. The green bar is as if we had just taken the edge TPU and given it high bandwidth access to memory, and then we so max. So it's not just taking the edge TPU and putting it near memory. That on its own does not solve the problem here. It's about co-designing the buffers and the data flow and all that as well. And with that in mind, in tow, we get this additional benefit from MENSA as opposed to just moving things to high bandwidth. And overall, with this design that we have for MENSA G, we're improving the throughput by 3.1x over the edge TPU. So there's a lot more information in the paper. As I mentioned, this is a collaboration with Google and with a number of my collaborators at ET in Zurich. This is in FastPath2021, and there's a whole bunch of information about the characterization and the architecture here.
So you studied this for edge, but it seems like the general techniques would be applicable not just to edge, but any sort of system in which one of these.
Absolutely. The downside, of course, is that people have a tougher time, I think, swallowing the pill that air is limited when we don't talk about edge devices, right? So there are still some people that will say, "Oh, sure, it's a server. Sure, we can give, as long as it's within 4 centimeters squared, go crazy," right? You're absolutely right that I always take issue with that because yields and costs all are associated with that area. And this certainly would be applicable, I think, in all those kinds of ranges. It is perhaps a little bit harder in large-scale machines for 2 reasons. One is that you have, all these models for the edge were already highly constrained to try to fit with edge devices. So even though there's a lot of heterogeneity, there's still some bidding that you're getting because you're usually trying to minimize the size of the models, even if that comes at a small cost of accuracy. Right? That's not necessarily going to be the case in large-scale machines, right? And so we have a much more diverse crowd of accelerators. So instead of having 3, maybe you'll have a dozen, right, or something like that. Just as a guess. The second thing is that a lot of the large-scale TPU-like accelerators are often trying to do training as well as inference, right? And so again, you could use heterogeneity to help with that, but that helps with a whole other can of worms in terms of the amount of traffic that you need and the amount of memory that you have. So I'm fairly confident, even though I've never looked at it, that for training, processing near memory is perhaps an even better tool to use, but it's often what we consider an offline cost. It's not nearly as it's harder to make that case for them when we have to do something like this. Awesome. So how are we on time? Technically 1 minute. Can I say about 5?
Yeah, sure.
Cool. So I want to talk quickly about the sort of second approach that we have. Right? So that was processing near memory. This is other idea of PUM. If you remember, just as a quick refresher, this idea of instead of having sort of CMOS-like logic, we're going to try to use the memory cells themselves to do some sort of useful work for us. And so to understand how that works, we're going to take a brief dive into non-volatile memories. Today, if you look at how non-volatile memories are organized, there are a number of ways to do them, but what we're going to look at is what we call a crossbar or a cross-point array, where essentially you have a whole bunch of column lines and a whole bunch of row lines, and at every intersection of a row line and a column line, there's a memory cell. And this memory cell can take on a number of different forms, but we're going to look specifically at ReRAM. In part, we did that because we actually had access to ReRAM nanofabs and to understanding device properties, so that we can actually co-design this better than simply just taking a table out of an ISSC paper and pretending as architects that we knew what we were doing when we looked at it. But to give you an example of what you can do with this ReRAM, I can take 3 cells that share a row line, and I can do a NOR operation. If I take these 2 cells and I float the voltage of the row line so that it'll behave as what I'm doing from the columns. and then I apply a specific voltage onto the column lines of my two input cells. This is essentially going to do voltage division, just like the Kirchhoff's voltage law. And so what I'm going to have here is that my floating line is going to have the NOR of these two cells on this line, and then I can ground the third cell's column line to reprogram it with the output of that NOR computation. I'm happy to talk with anybody about this offline, and in the interest of time, I'm not going to get into too many more details. This is actually possible reliably in many types of memories, both memories such as DRAM and SRAM, and newer non-volatile memories such as ReRAM, MRAM, and phase change memory. And this is just one example. There are a whole bunch of different computations that one can do with this. In fact, some of you might be familiar with, well, actually, I'll come back in a second. Sorry, I forgot I had this one slide. So I'm going to look for now in this digital domain, essentially using these Boolean operations to try to do useful work. Those are really amenable for things such as bit serial operations. Some of you might be familiar with the Ripple carry adder, where we compute one bit at a time, we generate some carry out, and we propagate the information to the next one bit adder. This is, of course, the most primitive way to make an adder, and as anyone who's designed an adder or gone through computer organization knows, we can do a lot better than this. This is the most primitive way to pass data. And that's one of the things with bit serial operations. We can do many different types of bit serial operations in home architectures, but they incur long latencies because they're sort of the most rudimentary way to do a lot of these operations. And so we make up for this by not operating on one pair of bits at a time, but we operate on columns of bits, where essentially we're doing vector operations with hundreds, if not thousands of words. I'll come back to that in a second. But one aside I want to have here is that some of you that are looking at machine learning might have been thinking, oh, processing using memory. He's surely going to mention what some people in the research community have been calling in-memory compute, where I treat new memories as basically matrix multiply processing elements. We decided to go a different route, and that's for one main reason. So when you look at this analog PUM that some people have been talking about, right? In fact, there are prototypes. This is what Mythic and its matrix processor are doing. IBM's Hermes, they're both doing these types of operations in non-volatile memories. But the idea here is that I have that resistance that my memory cell represents, and instead of having a single value like what we're doing for our NOR case, we can now store multiple values of resistances in that single cell. And then I have a variable voltage, and so I now have a multi-bit resistance that gives me a weight that represents one of maybe, let's say, 32 values, let's say 5 bits. Same thing with the voltage. You can take one of the 32 values for 5 bits, and I can do a 5-bit multiply. And there are architectures that essentially put all this together. And now this is using Kirchhoff's current law to be able to do the computation. The downside is that this requires ADCs and DACs to be able to convert from the voltage domain to the current domain and back. But moreover, this creates a lot of difficulties in making these devices. They can work okay for matrix multiplies where we can tolerate some approximation, and sometimes the errors we've introduced are good because they give us some basically randomization into doing our computations. But if you look at the actual device behavior, this is a voltage and current distribution. And this is a little bit of a toy example to make this clear, but we see a lot of nonlinearity. This curve actually goes like this and spikes up. And so in the digital domain, when it's a 1 or a 0, there's clear endpoints where we can gravitate toward here. But if I want to have, say, 32 different values to represent a 5-bit resistance, I have to find exactly where I'm going to fall along this nonlinear region. And that means that, unlike in CMOS circuits, it becomes very difficult to chop up the right windows and get the type of accuracy I want. You could be off by several bits if you're not careful with these types of circuits. So we decided to look at the digital world. Of course, the digital world is not free of problems either. Remember how I said we try to overcome bit serial latencies by doing hundreds of thousands of operations? Well, it turns out that if you put too many of these operations together on a single column, you'll eventually make the metal wires themselves break down. You're going to exceed the current carrying capacity of these wires themselves. So it's actually difficult to make these arrays larger than 200 cells by 200 cells on the side. If you talk to somebody who builds memories, that sounds crazy. We make large memory arrays so that we can amortize peripheral circuits so that we can reduce the amount of I/O and controllers we have. And so what we set out to do was to figure out ways in which we could buy back the performance with small memory tiles in practical to fabricate amortizable ways. And so I'm not going to go into too many details here, just in the interest of time, but we essentially found a way to distribute the bits of a piece of data where each bit is its own tile, and then we essentially did pipelining between bits. So instead of having to rely on the columns, we now we come back to old tricks that we used in computer architecture, but in new ways for bit serial computations. Essentially, if we add a buffer in between each of the tiles, when I'm doing a set of additions, I pass on the carry to the next tile. So I'm moving on from computing the carries and the sum for bit 0 to the carries and the sums for bit 1. While I'm doing that, these tiles in the back, since I've now isolated the bits, they're idle. So I can reuse them to do the next set of additions, the next set of other computation. And this is where a pipelining comes from. This bit pipelining is kind of neat, it's a neat little trick, but of course, it might be really difficult to build this in circuits, right? And people when they're doing this kind of work often overlook circuit level overheads. We didn't want to make those mistakes, so we actually sat down and thought through and designed at the transistor level all of the control circuitry to make this type of bit pipelining happen, where we could reuse instructions from tile to tile, and we could actually amortize the cost of these control units and the peripheral circuits across a very highly scalable unit. And so we designed this so that we could have essentially these racer cores, these vector processor cores that we could have. And we amortized 64 of them across a single set of peripheral circuitry and control circuitry for the bit pipelining. And I can have one of these clusters that has 2 megabytes of memory, or I can have 4,000 of them that will create an 8 gigabyte chip within a 4 centimeter squared area. And this, of course, we did this, keep in mind all of the thermal limits that we have in modern chips and all of that as well. So this fits within what we can build in a chip today. And you can see here that these bit serial operations can actually do a lot of useful work, right? It's not just additions, not just comparisons. We can do max, we can do trigonometric operations. These are all integer for now. We're looking at ways to develop floating point support for this. But we've essentially created a vectorized ISA that takes those NOR operations and builds them into a whole bunch of useful functions for many different types of applications. And so I'll speak to this just for the sake of comparison. We have some tools for actually modeling this from the circuit layer up, so the device level circuit layer up to the architecture that we've open sourced. But the bottom line here is that across a bunch of data-intensive workloads, including some that are for machine learning, we see 107x speed up versus a 16-core CPU. And we see healthy speedups over GPUs as well as in SRAM computing circuits as well. Essentially, we've introduced million-way parallelism in ways that we could not do before, but we can actually harness it thanks to the way we control our circuits. The thing that we really are interested about, energy, we actually do pretty well on that as well. We get 189x savings versus that 16-core CPU. 17x savings versus the GPU, which is designed for 1,000-way parallelism, but with different trade-offs. And the 30% savings over the improvement over the energy of that in SRAM. So, why am I mentioning all this to people that are interested in machine learning? This is all sort of, that's nice, but, Well, we wanted to do this comparison to that analog matrix multiply as well. Cascade is one of the state-of-the-art research approaches to doing that analog ReRAM-based matrix multiply. And if I forget what the exact numbers are, but it essentially is about an order of magnitude better than the TPU in terms of performance and energy efficiency, I believe. So that was our starting point that we used for our comparison. What we found was that our approach, which we called Racer, actually outperforms Cascade by about 3.1x on average for the machine learning workload that's capable. You can see that we do really well with our matrix multiply vectors and things like dense DFTs. With Lynette, we fall a little bit short, and certainly with sparse DFTs, we fall behind fairly. That's because we're not as good as exploiting sparsity in our current form as Cascade is. So it's not like there's an obvious win here. But by and large, we see that for the kernels that we're looking at, we actually are, we have fairly healthy benefits that we can get here. The other thing to keep in mind, though, is that this is designed with this idea of edge computing in sight, right? Cascade, the TPU, all these things are designed really for just matrix multiplies and neural network computations. Racer we looked at kernels from image processing, from we looked at machine learning, we looked at data analytics. It's essentially capable of much more than machine learning. So not only are we using these performance improvements, you have sort of a like a much more flexible data accelerator that can do ML and then some, which I think is something really important to keep in mind as you're thinking about these edge computing devices and types of little features. So I apologize that I sped through this a little bit, but just to make sure that we finish up the time, essentially the bottom line here is that we're now at a point where edge machine learning is really exceeding the capacities that that our accelerators are used to now. And so processing in memory offers us a way to be able to modulate some of those benefits and to actually get much higher efficiencies while introducing things such as heterogeneity or looking at things such as data accelerators for the edge that can also be able to help us out with machine learning. All right. There's more information in our papers if you're interested. I'm also happy to hang around and talk with anyone who's interested after the fact. But with that, I just want to give a quick shout out to people in my research group and to Owner Muklu's research group, folks at the CMU Data Storage Center, and people who have been supporting our research in some of this PUM stuff over the years. So thank you very much for bearing with me, and I'm happy to take any further questions you guys might have.
Further questions?
When you consider the PNM or some pumps,
Sure.
Do you think about to cooperate with some kind of accelerator near the processor, like GPU and your PNM?
Yes, so these works looked at the accelerators in isolation for the most part. But we've done a number of other works that have looked at doing this type of processing near memory. Well, I'm just going to say PIM because it applies to both types, where they work as accelerators that cooperate both with other accelerators on the CPU as well as the CPU itself. Right? And that introduces a whole host of other problems, such as how do we handle cache coherence? How do we handle virtual memory? How do we deal with scheduling things across all these types of cores? We've done some of that work. We have a paper from a few years ago looking at the cache coherence problem, how to solve it. We've been looking at doing virtual memory, and we have some things that we're hoping to come up with in the next few years that will tackle some of that fairly efficiently. One of the big areas that we in our group are looking at is scheduling, right? When you want to distribute jobs, that actually ends up becoming a problem that can go as far as the compiler, right? Figuring initially when you're compiling a program, what accelerators are best suited for what jobs. And that's an area that people have not really tapped very far in the PIM community. And we're actually hoping to build some of the compilers and the runtime software to finally make some of that stuff happen. So the short answer is that we've thought about it. We still have some work to go, but hopefully in the next few years we'll actually be able to make headway to have a full system that can pick which compute unit you move things onto, what the most efficient place to do computation is, how you virtualize that out to run multiple programs, and all of the stuff that we're used to in regular computers. Yes?
Great talk, thank you. I'm very curious about when you think about the future of edge machine learning accelerator, how do we actually leverage the unutilized resources to support multi-tenancy? Because I can imagine that more and more users with different latency requirements, for example, some self-driving car algorithm, they really need real-time latency, but other actual things like having battery latency tolerance. So when you are co-scheduling them into different machine learning accelerators or different design spaces, is for the architects, what kind of support?
Absolutely, that's a fantastic question. So there's two parts to that. Right? The first is, with Mensa and the runtime we talked about, while we have not looked into it ourselves, there is an easy way to extend that for multi-tenancy and to schedule multiple layers at once. For the interest of what we're doing, we're analyzing things one layer at a time, just to be able to this is actually the second point. The second point is that when you look at mobile devices and edge devices, it's unclear just how much multi-tenancy is going to be supported on them in the long run. Right? Unfortunately, we have this whole idea of foreground and background applications, and A lot of the influence that we're doing at runtime, things that need quick responses, are being done with foreground applications, right? And we still don't have a good way to run one or maybe two of those. That changes, of course, very dramatically when you go into server and even desktop settings, right, where multi-tenancy is very much a standard expectation. There may be, so certainly what we've talked about allows you to manage that multi-tenancy across accelerators. One thing that we did not look into that could be interesting is how to do multi-tenancy within a single accelerator, to virtualize out the buffers and the resources and things like that. It's the way in which we're doing our design, nothing prevents you from doing that if you could already do that in Accelerator today. But we have not introduced supports to make that happen either, right? And so you'd imagine that you have exposed some of that information to the runtime and a schedule to make all that happen in that heterogeneous C. So now it's not just what accelerator am I running on, but what portion of the accelerator am I consuming, right? But then we also need to think about ways in which we can adjust data flows to support that multi-tenancy. And I think that's one of the big hurdles that we face for efficient multi-tenancy in a lot of these types of accelerators today. And so I think it's an interesting area. We have not delved too much into that beyond some cursory stuff, but it certainly seems like it's possible. And if anything, I'd argue that that makes even more of a case for moving more of these things close to memory, because now you're going to have even more memory bandwidth issues as you're doing that context switching and trying to manage the more limited space you have in numbers.
Thank you very much.
Sure. I want to keep an eye on time.
Yeah, I at the risk of ruining the time myself.
Yeah.
How is programming of this? Can I just use my standard TensorFlow or PyTorch, or do you have to make changes to take advantage of what you do?
So for Mensa, we actually designed it to work with the existing TensorFlow compiler. So all it would do is just simply change the final backend targeting. We actually designed so that you could take existing TPU models and be able to put the whole method today. Unfortunately, while we normally like to open source things in our group, since we're basically trying to make our case with that with Google's compilers, we didn't get to release that. But yeah, we did this explicitly for Mensa under the assumption that the compiler would say the same. For Racer, it becomes a little bit more challenging. There are other works, for example, if you look at some of the things that Ritu Das's group has done out of the University of Michigan, they've looked at basically taking tensors and being able to compile them onto an SRAM computing. And we could probably use similar tool chains to be able to make things work on Racer. But Racer, because we're not just looking at ML, we really want to go beyond the tensor compilers and actually look at general purpose computing compilers for that. None of that exists today, right? That's actually one of the areas that we're working on. Like I've got a number of students that are looking at how to develop that tool chain from programming models, how to use existing data parallel programming models to leverage these types of chips, down to how we do the compilation for them, how we do the scheduling of them, how we can actually support some sort of multi-tenancy on that PUM chip, and virtualize out the resources. So not yet, but hopefully within about 5 years we have some answers to that.
Very nice, and someone, things go really well, you're sort of forming a foundation of a new type of nice.
Yeah, well, and actually that's one of the big things. I actually mentioned this at the PIM2 talk yesterday. I think we're at this point, and as a community for PIM, where we need an ISA. We don't have that today. Everybody makes their own examples, and that's not good for systems tools. It's already hard to convince software programmers that they need to write system tools for imaginary hardware. That's already a hard sell. It's even harder when you tell them, oh yeah, take your bet. Also, this might not win next year, right? I'd love to think that we designed the winning architecture, right? That would be great, but I'm a pragmatist. That's not likely to happen, right? So it's better for us to develop software tools with a common ISA that can sort of target everything else. We've done this for decades. There's no reason we can't do this for kids.
Great, lovely talk, over the stuff, thank you.
Thanks, Todd.